All right, so I'm on pages 25 through 30, chapter 2 of Tom Mitchell's Machine Learning. And there are three algorithms for finding the best, for finding a hypothesis within a hypothesis space. Um, and the examples that they use are what is what is it again? The example is not the probability. Hold on. Oh, days on which my friend Aldo enjoys his favorite water sport. And that is determined by 6 attributes: sky, air temp, humidity, wind, water, and forecast. And then you have the enjoy sports attributes to say whether he enjoyed it or did not, for the training. So there's 3 algorithms. The first is find S. This is basically finding the most specific hypothesis that categorizes the training examples. And it starts with the most specific hypothesis, which is the empty sets, or not the empty set, not the null sets, the dead set of zeros with a slash through it, or theta, I guess. Basically saying it doesn't matter what you put in here, everything is a negative example, which is too specific, obviously. And then it takes its first training example and gets as specific as that. So, for example, maybe the training example is sunny, warm, normal, strong, warm, sane. And that's the different attributes, right? Like the air temp, the wind, etc. And then it's just that specific. That's basically the hypothesis, is that specific example is the only example in which Aldo enjoys his favorite water sport. And then it's given a second example, and it tries to generalize between those 2 examples. So it comes up with a hypothesis that fits both of those examples. Maybe it's that the wind could be strong or weak, right? And if there's only 2 values for wind, then it puts a question mark where wind is, right? Because it could be either, it's the same hypothesis, except it changes wind to the wind could be anything, doesn't matter. And it keeps doing that until it gets through all the training examples. The only problem with find S is that it ignores every negative example. It's only tuned to positive examples. So if you give it, I don't know, something that doesn't fit its criteria, and it's a negative training, basically, Aldo doesn't enjoy his favorite sport, the hypothesis just doesn't change because it's going off positive examples. So there's that. It also only finds one hypothesis that fits all those training examples. In a real life situation, there might be many hypotheses that within a hypothesis space that correctly classify all the training examples. So that's basically the find S algorithm. I'm trying to see if there's anything else. Some questions you might have. Has the learner converged to the correct target concept? It has no way of knowing based on this that new training examples could make it more general, right? Like if it's gone through 5 of them or 10 or whatever, and none of the training examples have challenged the algorithm to be any more general, then it'll stay as specific as it is, and therefore might classify a more general, not a more general, but might classify an instance as might classify an instance incorrectly. There's another question: why prefer the most specific hypothesis? Because there could be a more general one that covers all the training examples and future examples. You also have to assume that the training examples are all consistent. So you have to assume that given just these 6 attributes, air, temp, water, whatever, like we don't include Aldo's mood in that, in which it could be a sunny day, air temperature is nice, whatever. He's just in a bad mood, so he's not going to enjoy his favorite water sport. You have to assume in this example, or using this algorithm, that that's not possible. So that all the training examples are consistent. And we know in real life it doesn't actually work that way. And the preference would be to have an algorithm that could detect inconsistencies, like that could say, wait a minute, you've got an example here and an example here that are basically the same, but one is negative and one is positive. This algorithm can't do that. And it also cannot converge to more than one maximally specific consistent hypotheses. There's a world in which Aldo can have 2 very specific instances in which he likes his favorite water sport. They can be equally specific but different. And this algorithm is only going to find whatever one it comes across first. It's not going to find the other one. So there's that. Then you have the candidate elimination algorithm. This is a second approach. It addresses a lot of the limitations of find S. For instance, it can output it. Let me see if I get this right. It describes all the hypotheses within a set that would fit the training, would be consistent with the training examples. And it does it in more general than partial ordering, which is something that I talked about before. So let me find exactly what it does. So it goes sorry. Um, so what it does is it just eliminates anything that doesn't fit the training examples. Um, yeah, it eliminates anything that doesn't fit the training examples and leaves everything else. So it doesn't start with one specific hypothesis and make it more general until it converges to um, um, a general hypothesis. Um, what it does, yeah, and it doesn't explicitly enumerate all of its members. So um, um, it doesn't list like it doesn't. And we're about to get to. I'm about to get to this in a second, but I want to make sure that. Yeah, so this is what I was looking for. This is actually on page 32. And it starts by taking the most general hypothesis, which is all 6 attributes are question marks, and it takes the most specific hypothesis, which is that all 6 attributes are the 0 with the slash through or theta. And then, so it sets those boundaries. And then, as each training example is considered, the most general and the most specific are generalized and specialized. So it specializes or makes the most general hypothesis more specific, and it makes the most specific hypothesis more general until you end up with a version space that is consistent with the training examples. And that's how the find S algorithm, or sorry, the candidate elimination algorithm works. So there's that. You then have the list then eliminate algorithm, which is super easy to understand. It basically lists all possible hypotheses, and then anything that's inconsistent with the training data, it just eliminates it. This works if your hypothesis space is finite. It doesn't work if it's infinite. So, for example, I don't know. I assume continuous a continuous distribution of attributes, or within a single attribute. So if you're for air temp, if it's not categorical, which is finite, and it's continuous, which is it goes from I don't know 64. It goes from however many degrees it can be on Earth, which is I don't know let's say negative 100 Celsius to 100 Celsius, even though that's not true. Within that, there's an infinite amount of numbers that could be between, not numbers, but decimals, that could be between negative 100 and 100. You could have 64.4, etc. So it would not work in that kind of situation, because then it can't lists all the possible hypotheses. But in one where you can list them all and you can list them in a relatively low computational way, the list then eliminate algorithm would work. And it's guaranteed to output all the hypotheses consistent with the training data. It's just not realistic for most, actual problems, because you're not going to get this nice clean data. So yeah, hopefully this video helped. It definitely helped me to explain it to myself. Yeah, and catch me in the next video.